Okay, so plan for today. We'll spend some time talking about the final exam. My goal is to talk about logistics and then give you guys a brief idea about format of the exam. And then we will start talking about Z transform. And then wherever we end at the end of the class, that is it. That's where we end. I have more planned than we have time available. So we'll have to abruptly end at some point. So let's do final exam review first. So this is Thursday, August 19th. Where is it? When is it? It is from 10:30 a.m. to 12:45 p.m., exactly the same time as we had for the previous two exams. It is going to be offered during class time, offered both in person and online. So whoever wants to be here in the classroom can be here. If you have a Fields and Waves exam or Kano's exam, whatever exam you may have, and if you are in person for that exam, I'm giving you this option so that you don't panic about travel time. Right? You can stay back in low. You can. I don't think there are going to be more than 35 students who are going to need that accommodation. But even if there is, we have enough seats, so we'll be fine. So you can take it in person or you can take it online. If you are going to be in person, then I will be proctoring you in person. I'll be here as well. And if you are going to be online, then I'll be proctoring you through your webcam and microphone, exactly as I did for the previous two exams. So if you're in person, if I were a student, I would be in person because it saves me scanning and uploading time. Open book, open notes. So you can bring in resources over here. You can bring your laptop with you. You can bring in books or crib sheets, whatever you want over here. You don't need to bring in any tables because I'm going to print that and give it to you. So you don't have to print those for yourself. And if you're taking the exam in person, like I said, you don't have to scan and upload. So you may save about 10, 15 minutes, depending on how you do it. So after the exam, I will scan and upload the exams for you on Gradescope. If you're online, however, still open book, open notes, but you will have to take care of scanning and uploading. And while you are uploading the submission to Gradescope, make sure that you do it properly. You check it after submission. You map the pages to the problem numbers correctly. In other words, the responsibility of the submission going through okay or not falls on you if you're taking it online. So offered both in person and online. In person is probably a better option because of that saving time. Go ahead. No. I'll literally give you the exam with spaces like a traditional in-person exam. You have taken those, right? Oh my gosh, really? How about Fields and Waves? I thought you guys were doing. Oh, okay. All right. So the exam that is going to be in person is going to be literally like old times, like 13, 14 years ago, the way you used to conduct exams with questions in the space underneath the questions to fill in the answers. That same way. We have had more online college than in person. Yeah. So sure, if you want to be in person, be in person. If you are preferring online, prefer online. But I can tell you one data point from another class that I teach this summer. Invariably, people who take the exam in person get a higher average. Yeah, so not just the classes. When you're taking the exam, I gave the students the option, wherever you want to be. And people who chose to be in person invariably scored better than people who chose to be online. That's just correlation or causation. I have no idea. I would hate to pick one or the other. I'm just providing you the data point. All right. What is allowed during the exam? Well, hard copy. Well, let's talk about what is not allowed in the exam. Not allowed is calculators, electronic devices. If you're using your iPad to just view Piazza resources, that's fine. But I don't want you guys to be putting on headphones or earphones, using electronic devices, other than using your laptop or your iPad to view Piazza resources. That is fair game, right? Looking up Piazza resources is fair. Looking up your handwritten notes, textbooks, all of that is okay. But using MATLAB or using a calculator, looking up things online, those are not okay. People who are online need to look at this particular resource. This is going to be important. And they're already there on Piazza. Download them. Make sure you know exactly which table has what property, which standard pair you're going to need, because you will need to refer this particular resource many times, as you must have done for exam 2. Let's see, Fourier transform tables, yeah, hard copy books, not allowed, proctoring, asking private questions, no crying allowed. For online students, as before, use your mic and camera, keep them on during the entire duration of the exam, 2 hours, 15 minutes, so that you can be proctored. I'll be the only one who will be listening in on that. I would expect everybody else to have their computer volume turned all the way down to 0. While I do this, I will be in the classroom. So I'll be proctoring in person and online at the same time. Let's talk about the content. So it is going to be comprehensive, but if I say signals exam is comprehensive, some of you might panic. If I were a student, I would panic too, because there's a lot of things that we went over. So what I'll do is I'll talk about some, so this is not a complete list, but I'm listing out all the things that I find are going to be more important. So if you have some amount of time that you're dedicating towards preparing the final exam, I would dedicate on these topics first. So signal operation, comprehensive exam essentially means from start to finish, right? So it's not going to be, as opposed to what? As opposed to only having an exam over material from exam after exam 2. This was a rhetorical question. All right. All right. Yeah. Okay. So good. That's excellent. So comprehensive exam means a cumulative exam. Signal operations and representation. Those 3 operations: time shift, flip, scale. The order of these operations. Definitely, there is a short problem asking you to do those operations, right? So given a particular, I can express the signal in few ways. I can sketch it. I can give you it in the bracket notation. So depending on one way, I can express it and I can provide that signal, and I can say, all right, do these particular signal operations on this, and maybe provide the answer in bracket form or as a sketch. Or to make it a little bit more interesting, and if the signals are more appropriate enough to be expressed in terms of unit steps or ramp functions, I may ask you to express, after you do that signal operations, represent the resulting signal in terms of step functions or ramp functions, so that there's a clear short answer question about that, no points for guessing. Next, convolution. There is going to be a long answer question about continuous time convolution. Pulse train? Pulse train, that is, all right, pulse train with another pulse train. Oh, that's nice. Yeah, one pulse train getting convolved with another pulse train with different widths and heights. So you start getting pulse trapezoid trains, right? Yeah, so, well, not that. That is a little bit too easy. So continuous time convolution, you will see now what kind of signals you might see. Remember, this is graphical notation, or you'll have to sketch it case by case, which essentially means that the signals cannot be too complex. You can get exponentials, pretty easy to integrate over them. You can get linear functions, or you can get constants, or impulses, right? So these are the 4 options there: exponentials, linear functions, constants, impulses. And you'll have to play along with that. You're not going to be going over quadratics and higher order functions of t, because then when you come to integrations, then it's going to be a little bit tricky. But there is a continuous time convolution problem on the final exam, which is good. Very good question. So I will state that explicitly in the problem if I want it to be in a particular form. So, so here, the final exam, what I'm looking for is this. What I'm looking for is, this is the course, right? These are the set of topics that is defined, that defines this course. Does the student have expertise in those areas? So in exam 1 and exam 2, there were lots of tricks in the problems, right? Like, this is not going to be as tricky. This is going to be more straightforward. Can you solve this problem? Can you convolve this? Because I'm trying to go for checking your understanding about a particular concept or technique, I'm going to sort of box you in there. But you are right. There are other ways of doing the same problem. And you can use that to validate your results. So work in one domain, use the other domain to sort of make sure that you got your answer consistent with the one that you got, right? What you expect. Sorry? Oh, cases, right, for convolution? Well, okay, here. Cases, the way I look at it, cases is this. Inside the integral, I have 2 functions that I'm multiplying. Every time my function is going to be different, I need to use a different case for it. If some functions are not changing at all, I can use that as the same case. That's the simplest way of looking at it, I think. But yeah, you're right. They can get tricky. If the signal is changing shape a lot, well, words, both signals are changing shape, then you're going to get a lot of algebra to do. Now, what do you do when you get stuck? When you get stuck with algebra, what do you do? Well, sketch is one. So here, what you can do is provide the cases, provide the integral, and if you don't have time and you're in a rush, maybe skip over the last part. Because what is more critical in a convolution is to set up the ranges of the cases properly and be able to set up the integral properly. Solving that is not that critical. And to help you out, I'm giving you guys some simpler functions in time, so you should be able to deal with that. Andre asks a question, is it straightforward like exam? No. Exam 2 was straightforward. What? Well, here, I thought so, but the results didn't support that. So because the results didn't support that, I'm going to not assume that it was simple. Right, yeah. So when I wrote it as a more straightforward exam, but it didn't turn out to be that way. So let's just forget that I said that. But for the final exam, my intention is going to be here, straightforward problem, can you solve it? Straightforward problem, can you solve it? Right? So it's going to be essentially, softballs that you can knock out of the park if you just know how to deal with those things. Was that? If you know, no, it's not going to be tricky, right? Like, that's what I'm saying. It's not going to be tricky because the goal is not to trick. Yeah, exam 1, exam 2, we could do it. Not for the final one. Let's see, convolution, Fourier series. Yes, a short answer. most likely a short answer problem there about, this is a periodic signal, can you find the Fourier series coefficients? You will have to use certain properties of Fourier series to get there. Next, Fourier transform, finding the Fourier transform of a signal using the tables. Most likely a longer question there about signal is given either in time domain or in the frequency domain. You may have to use duality or not, but I'll give you the duality property as a reference. But getting to the Fourier transform or the inverse Fourier transform, something similar to what you might have seen in exam 2. So if Fourier transform is something that is not your strength, just go back and take a look at what we did for exam 2 for the problems that were assigned to you. And of course, I have got several back exams that I posted for you to look at as a reference. But Fourier series, Fourier transforms, questions are going to be there. Signals given, can I find Fourier series? Signal given, can I find Fourier transform? Or spectrum given, can I find Fourier time domain signal? That's exactly what someone making a tricky exam would say. Fair point. The output is going to be, yeah. So sketching, right. So expressing your results as a sketch is turns out to be faster in most cases. So that's something that you can do on your own, right? If I say, all right, here, express your answer in this particular format. If you're not going to be able to do it using ramps, at least provide it as a sketch so that you get partial credit for it. About how many questions? Oh, yeah, I'll be, all right. So you guys are in a hurry. All right, next topic, communication, sampling, and reconstruction. So given block diagrams, there's a transmitting message to be sent, goes through certain filters and product multipliers, goes through the antenna, gets transmitted. At the receiving end, if it is sampled, it gets reconstructed, and out you have m hat of t, which is close to m of t, right? So dealing with block diagrams which have multipliers, local oscillators, samplers, reconstruction filters, ideal low pass filters or band pass filters, how are you going to work through that? Essentially, it'll boil down to this. At every stage, do I work in time domain or frequency domain, right? So that kind of assessment, oh yeah, this is a rectangle in frequency, easier to multiply in frequency and then move on, right? So being able to go from time to frequency, depending on what is more convenient, and tracking the signal from input to the output. That's what that last block is, communication, sampling, reconstruction. Next, response of LTI systems, extremely important topic. Essentially, if signals and systems had to be a different name, it would be that, response of LTI systems. So the concept of superposition, and I already talked about this, choosing one domain to work with, time or frequency, finding the impulse and step response. There's a relationship there, which is of a derivative. Next, Laplace transform in an ROC and its inverse. There will be a long problem on this. Laplace transform, using partial fraction expansion, break it down, talk about the inverse, inverse Laplace transform of that, depending on the signal being left-sided, right-sided, two-sided, and finite duration, you would find the ROC. Sketching the pole zero diagram and then shading out the ROC, things like that. Definitely there, no doubt in my mind. Next, Routh-Hurwitz criteria to comment about stability and sketching out the root locus. There's a long problem, long question, maybe 10 points on sketching the root locus of a feedback system. So your feedback system will be given to you as a block diagram. Look at that, look at the characteristic equation, look at how put out the poles and the zeros, using the rules of this, using the rules we laid out for the root locus, sketch out the root locus. You will have to find asymptote location, asymptote angles, all of those things. Anybody looked at the practice problems for root locus? All right, so if you have time, take a look at those. It's a good list of problems for root locus. It'll give you a good idea about how you deal with those kind of sketches. Next, Z transform and ROC and its inverse. So we are going to talk about Z transform today, but what I'm hoping that you get from this is Z transform is exactly like Laplace, but for discrete signals. So whatever you learned in Laplace is going to translate directly to Z transform. The only difference being now we are dealing with discrete time signals as opposed to continuous time signals. So it will still have Z transforms, Z tables, partial fractions, pole locations, ROC, exactly the same as we did for Laplace. So it's sort of the same things, but for discrete time signals. Let's see. All right. So these are about how many questions? I'm going to talk about that. But those are your. Oh, all right. That's it. Now, how many questions are going to be there? I will generally plan for about 5 or 6 short answer questions and about 5 or 6, maybe a little bit longer, right? So five short, then I'm going to pad it up with about 7 long answer questions. So the long answer questions, you know a lot of them already, right? One on Z, one on root locus, one on Laplace. Let's see, response of LTI systems is going to be there. One on convolution, one on Fourier transform. You already know the long questions now. The short answer questions are going to be appropriate for singular operations, representation, Fourier series, maybe discrete convolution, maybe Nyquist rate, response of LTI system, impulse and step response, those kind of topics, right? So wherever there is but I'll try to pick from this set, is what I'm trying to tell you. So I feel like I've already given you guys the question paper. Now it's just going to be me trying to figure out what numbers we need to decide. Right? That's the only thing that is left. Okay, so I'm going to stop recording here unless you guys have any questions. Stop recording here for the final exam review, not for Z transform. Okay, so I think we are ready to move on. Okay, so